Hey folks, as the title says here, this lesson is going to be on unit conversions or dimensional analysis, also referred to as unit analysis, and also on scientific notation, also referred to as exponential notation. And I'll probably just use all of those terms interchangeably. So it is kind of important to be able to convert from one unit to another. It's also important to make sure you're choosing a reasonable unit in the first place. So for example, if you're talking about how much gas you're putting in your vehicle, it wouldn't really make a lot of sense to talk about putting so many milliliters into your car. A more reasonable unit would be to talk about liters, which is what we do. So yeah, it does need to be a reasonable unit, just like I say here, if you're talking about distances traveling, say, between Calgary and Vancouver, it doesn't make any sense to talk about a measurement being in something really, really tiny, like millimeters, or something way, way too big, the average distance between the Earth and the Sun, astronomical units, kilometers, is what does, of course, make the most sense for that kind of a measurement. So at times, yeah, what you might have to do is do a conversion, a unit conversion, going from one unit to another. So for starters, the units do have to be of the same measurement type. So for example, we can't talk about taking meters, which are the units for distance, and converting it into grams, which are the units for mass. You can't do that sort of a conversion. But what you can do is milliliters into liters. They're both measuring volume. You can do kilograms into grams. They're both measuring mass. You can go from meters to kilometers, or we can kind of mix it up as well, and we can go meters per second, which is for speed, to kilometers per hour, which is also for speed. So these are unit conversions, and we use a process called unit analysis or dimensional analysis in order to do that. So you do have on your data sheet a kind of conversion table that looks similar to this. So what it does give us is a whole bunch of symbols, what those prefixes do represent. And it does show us here exponential or scientific notation as well. So right in the very center here where they do have this 1. So the prefixes that we have along the left-hand side, if someone says you have kilo, that means that you have 1,000 times whatever it is that you're talking about. So if we're talking about grams, and then we have a kilogram, that's 1,000 grams. If we have meters, and then we're talking about how many kilometers, there are 1,000 meters in a kilometer. Kind of works in the opposite direction as well. So if we talk about millimeters compared to meters, that is now 1,000th of a meter. If we talk about micrometers, that is 1,000,000th of a meter. So you can use this table for the prefixes and also for scientific or exponential notation that we'll get into here as well. So the metric units that we do use. In fact, we don't even use all of them for this course, but some of them that we will. The standard, or what we call base unit for length, is the meter. The standard or base unit for mass is the kilogram. Standard or base unit for time is second. Standard or base unit for volume is the liter. And of course, we've already come across this one here before for the amount of a substance, moles that we do have. And for temperature, it's actually measured units of Kelvin rather than Celsius. Those are the base units. So the method, how do you actually go about doing these unit conversions? So if you are converting to a unit that is larger, I'll give you a couple of strategies here. So if you're converting to a unit that is larger, we're going to move the decimal to the left. So let's say, for example, we have 120 meters, and you want to convert it to a unit that is larger. So kilometers are larger than meters. So what we're going to do is we're going to move the decimal to the left. The number of positions that there is in the difference between the two units. So if we go back to that conversion table for a minute here, so our standard base unit that we would have for meters is this one here, and then we have our kilo for kilometers. So what is the difference between these? Well, it's 1,000 times difference, or 3 decimal places. And if we take a look at the exponent here, exponential or scientific notation, you notice that there's a 3 here as well. 3 here, 3 here. That is how many positions you're moving the decimal place. So if we're going from something that is small to something that is larger, we're going to have fewer of that larger unit, and that's why we're moving the decimal to the left. So right now the decimal is right here. That conversion table told us that we have a 1,000 times difference between meters and kilometers. Kilometers are the larger unit, so we're going to move the decimal over 1, 2, 3 positions, and then we would end up with 0.120 kilometers. If you're doing the opposite, so if you're converting to a unit that is smaller, then we're going to move the decimal to the right. So let's say now that we have kilograms, and we have 14.7 kilograms, and we're going to convert it into a unit that is smaller. So what do we mean by smaller? You can fit many, many, many more grams into kilograms than, well, kilograms into grams. So again, the conversion factor here is 1,000. Once again. Only now we're going to be moving the decimal in the opposite direction. So if you are converting to a unit that is smaller, grams are smaller, we're going to move the decimal to the right now, the number of position differences. So again, it's going to be 3. So we're going to move the decimal place over 1, 2, 3. So I actually need to put in some extra zeros here, 14,700, and I'm going to move it over 1, 2, 3. So that ends up being 14,700 grams. Of course, we would probably have to write this as well to the correct number of significant digits, but we'll just leave it at that for now. So that's one way to go ahead and do these unit conversions. I'll give you some other strategies as well for how to go about doing that. So this one here is for distance. So we're converting 1.65 meters into centimeters. So kind of think your way through 1.65 meters. That is my height. And that's probably, kind of close to your height as well. So we're going to convert that into centimeters. So remember that meters, they're kind of big. And centimeters, well, they're considerably smaller. So if we convert meters into centimeters, we're going to get many, many more. There are many, many centimeters that you can fit into a meter. In fact, it's 100, of course, centimeters that you can fit into a meter. So yes, centimeters are smaller, so the decimal is going to be moved, in this case, to the right. So we'll end up having a bigger number. Let me show you another way to do this. So if we start point 1 with 1.65 meters, what I'm going to do is I'm going to multiply it by something, which is a fraction. And this is going to show the ratio of meters to centimeters. So the idea behind this is, even though we don't write this as a fraction, it's as if this is over 1 as well. So what I want to do is get rid of the meters, and I want to change it into centimeters. So if I want to get rid of meters, I'm going to multiply these meters here by something that has meters in the denominator. So the reason behind doing this is, if you do that, then your meters are actually going to cancel out. But what I want to end up with is centimeters. So I'm going to put centimeters at the top. So now you need to think your way through this way. In 1 meter, how many centimeters do I have? Well, I have 100. 100 centimeters per 1 meter. That is the ratio that we do have. So now I'm just going to multiply these two numbers together. 1.65 times 100 And of course, that's the number right there that we do end up with. So a couple of different strategies. You can just think about moving the decimal. It's probably better in the end to actually show all your work like this so you truly understand, and so you're not making mistakes and moving that decimal in the opposite direction. So here we're talking about volume. So we have 12,345 milliliters. So these ones here are small, whereas liters are bigger. And here, like we saw earlier, is a 1,000 times conversion factor. So liters are bigger, so we're going to move the decimal to the left. So right now the decimal is right here, so we could just simply take it and we can move it over 1, 2, 3 places. And that would be our answer. 12,345 milliliters is 12.345 liters. So another way to think about it is to kind of set it up as that ratio again. So we want to get rid of milliliters. In 1 milliliter, we have this many liters, 0.001 liters. And then you end up with that answer, converted to liters. So a couple different strategies there, and really important, ask yourself the question, always ask yourself the question, does it actually make sense? So if you are told that this is the distance here, which is about the distance between Calgary and Vancouver, and if you do your unit conversion into meters, and if you get an answer that's just over 1 meter, so does it really make sense that the distance between Calgary and Vancouver is just over a meter? Obviously you did something wrong, and what that is you moved your decimal in the wrong direction. So if I want to take 1,073 kilometers and convert it into meters, I don't move the decimal to the left that gave us this incorrect answer. You actually need to move it to the right. Always ask yourself that question. You will have to do this as well. You'll need to convert 2 units at kind of the same time. So you can try and do it all together. It might be easier to just convert one and then convert the other one. So this is a good example here. Quite often in physics, we do measure speed in meters per second. But of course, if you're driving on the highway and you see a sign which tells you the speed, it's kilometers per hour. So how do we convert between these two? So probably best to just convert one first of all, distance, and then convert the time next. So how do we do that? Well, kilometers, of course, are larger than meters. So we're going to move the decimal 3 positions to the left, or 3 places to the left. So here, we're only converting the meters to the kilometers. So if we have, let me just write this up above, 70 meters, and we want to convert this into kilometers. In 1 kilometer, we have 1,000 meters. Meters cancel out. 70 divided by 1,000 is the 0.70. So now we're doing good. We converted it from meters per second into kilometers per second, but now we need to convert the seconds as well. So hours are bigger than seconds. So if we wanted to sort of think our way through this, so if we're going this far in a second, in an hour we're going to go a lot further. So how much further are we going to go? Well, we know that there are 60 seconds per minute, and we know that there are, it should be 60, and we know that there are 60 minutes per hour. So if I do some sort of canceling out here, multiply those together, we end up with 3,600 seconds per hour. 3,600 seconds in an hour. So we're going to take that 3,600 seconds per hour, multiply it by our number that we just calculated, 0.070 kilometers per second, and then we end up with the speed here. I'm just going to show you how to do this all in a big line as well. Some of you might be comfortable doing this, others may not, and you might have to do it step by step. So if we start with our 70 meters per second, I'm going to write it like this, just to make it a little bit clearer. 70 meters per, I'm even going to put 1 per 1 second. So first thing that I want to do is I want to get rid of these meters. So I'm going to multiply by something that has meters in the denominator and kilometers that I want in the numerator. In 1 kilometer, I have 1,000 meters. Now, all in a long chain, I want to deal with the seconds. So I want to get rid of seconds. Here I have seconds in the denominator. I'm going to put it in the numerator. What I want to have is hours. In 1 hour, there are 3,600 seconds. So let's cross out some of the units here that we're getting rid of. So if I have meters in the numerator and the denominator, they cancel out. If I have seconds in the denominator and the numerator, they cancel out. What am I left with for units? Kilometers in the numerator, hours in the denominator, and that's exactly what we want. And if you just go ahead and plug these in a long chain, 70 times 3,600 divided by 1,000, I'm assuming we'll end up with the same number, which is the 252 kilometers per hour. So a few different strategies for how to go ahead and do that. Scientific notation or exponential notation. So we did see a little bit of this when we were talking about significant digits as well, and recording numbers to the correct number of significant digits. So just a quick little refresher on that. If we do have a number that is 3.36492, actually let's get rid of that decimal, let's just make it a big number. Let's say we have 336,492. But let's say that the original numbers that you had in your calculations only had 2 significant digits, and you were doing a multiplication calculation. That means that your final answer can only have 2 significant digits. So how can we possibly write this number here with only 2 significant digits? Well, there's actually only one way, and that's to write it as scientific notation. So right now the decimal is right here. Scientific notation does this. We're going to move the decimal over so it's after the first digit, which sometimes could be a 0, but we want to move it after the first non-zero digit. So the first non-zero digit here is a 3. That's where I'm going to move it. And I'm going to count 1, 2, 3, 4, 5. I moved it over 5 places. So 5 is going to be important. So now I'm going to round this to 2 significant digits. Following the rounding rules, that would be 3.4. And then to write it in scientific notation, I'm going to go times 10, and then I'm going to use this 5. So this 5 says I moved the decimal over 5 places to the left. And because this is a positive exponent, this means that it's kind of a big number. So in science, we do deal with some big numbers, really big numbers, and we do deal with some really, really small numbers. So if you think about one of the biggest numbers that we've dealt with, that is Avogadro's number, which is 6.022 times 10 to the 23 number of particles of whatever it is. This is a really, really big number, and we just don't want to write all of those digits, so we write it in scientific notation. So because this is a positive exponent, this is a really, really big number that we do have for that positive exponent. You can have some other numbers that are quite small numbers. So the mass of an electron, for example, is a fairly small number. It's much, much less than 1, so you would also write it in scientific notation. Okay, so back up to what we have here. So for some measurements, base metric units are preferred. and this might require the use of scientific notation for very large numbers and very small numbers. That's really the key. Very large numbers, very small numbers, and also to record, as I tried to show you up above, to the correct number of significant digits. This is why we use scientific notation. So general pattern that we have here, x times 10 to the exponent n. So x is the number with only one non-zero digit to the left, non-zero digit. So my number to the left of the decimal is non-zero. To the left of the decimal is a non-zero digit. And n is the exponent, which can be either positive or negative. So if it is positive, that's going to be a really big number. And if it is negative, then it's going to be a really small number, or at least a number that is considerably less than 1. So yeah, here's Avogadro's number. I'm only giving it here to 3 significant digits for this one. But the n in this case is a positive number. So that means that it is a really, really big number. I also give you here another example, the average distance between the Earth and the Sun. It's a really big number as well, measured in meters, so we write it in scientific notation. And the mass of an electron that I mentioned, really, really small, and that's a negative exponent. So what does it mean to write it in scientific notation? Well, this number here, the 1.5 times 10 to the 11 meters, the average distance between the Earth and the Sun, means that the decimal is moved 11 positions, 11 decimal places to the left. So the original digit was right here. So this is the distance in meters, the average distance between the Earth and the Sun, and we're going to move this decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's just after the first non-zero digit, which is the 1. So that's where we get the 1.5 times 10 to the 11 because we moved it 11 places. For this number here, that's a whole bunch of zeros that I've written here, but it means that we're moving the decimal, this should be 28 places to the right. So if we count all of these over, all the way to this position right here, that should be 28 positions that we're moving it. So yeah, as I've written here, it should kind of be obvious why you probably want to write things in scientific notation rather than writing all of those digits. So yeah, a couple of things to remember. Really big numbers, they have a positive exponent. Really small numbers, they have a negative exponent. And I just want to show you on your calculator as well, on the TI calculator, how you can plug in some of this information. So let me just go to the internet even and just pull up a picture of the TI calculator. Get a picture of one here so I can show you a couple of the buttons on the TI calculator. Again, there are different ones that you can take a look at, different graphing calculators. Let's click on the most expensive one here from Best Buy. Take a look at this graphing calculator. So a couple of the buttons that you'll notice on here. So using the second function button, yellow one at the upper left-hand side. And then the log button as a second function is 10 to the x. You can use that one for scientific notation, and you can also use this one here, the second function EE. You can also use that one for writing scientific or exponential notation when you're plugging these numbers into your calculator. So if I do want to put in, for example, the 6.22 times 10 to the 23 for Avogadro's number, this is the process that you could go ahead in terms of plugging this into your calculator. Okay, so first of all, you're just going to put in 6.22 And then from there, you can hit the second function button. You can do the one that is the EE. You can then put in your 23 and press enter. So I'm just going to show you exactly the way that this just show up on your calculator when you do go ahead and do this. So it'll show up as 6.22, and then it will have a capital but kind of subscripted E, and then 23. So that is 6.2, should be 6.022, sorry about that, 022 times 10 to the 23. I need to squeeze in my 0 here for all of these because I missed them, didn't I? Okay, another way to do it is we put in the 6.022, go second function again, and now we go to the one that is the the log button, which as the second function is 10 to the x. And again, you're just going to put in your 23. You're going to press enter, and then let me show you again how it actually shows up on your calculator screen. So you might eventually get it this way as well, and when you enter it in, it might come up as this. Hello. This is the way it should show up, which again means the same thing. It means 6.022 times 10 to the 23.